Hi, welcome to this fourth video in Bayesian statistics. Well, of course, I'm going to talk here about machine learning. And at the moment that I'm going to start this video, it might be good. We have now done roughly half of this course to recap a little bit of what we have done so far. Now the last video has been essentially about an intermezzo of non-parametric statistics. But what I've said before is that we have been looking at an introduction to supervised machine learning. At that stage, I said that what we basically do is that we're going to look at the principles of machine, or maybe better to say, supervised machine learning. Well, and at that stage, I said that things are going to be really theoretical. But at the same time, I did say, or at least promised you, that at a particular moment in time, I'm going to look at applications. I'm more going to look at the algorithms. And that day actually has come. Today, we are going to look at our first application or our first series of algorithms. And that is related to what is written over here, supervised learning for regression models. So we're going to look at regression models. Well, that looks very familiar to you as econometricians, actually does, but we will see later on that I'm going to tell you some things, at least I hope that I tell you some things that are going to be completely new to you. But let's start with things that are very familiar. Well, what we already know is that we have an outcome variable, yi, that we would like to predict, and we typically have a large set of features, this xi that we have over here, where I is going to run from 1 till n, and we're going to have this assumption of iid. There's nothing new with respect to that. And let's start actually to recap a bit of what econometrics is about at the moment that we're going to look at a regression model. In econometrics, we should realize that we usually talk about the so-called true model. That means that we have at the left-hand side here yi, and at the right-hand side we have xi beta plus ui. Well, we'll later on see that this is also going to be the starting point, of course, for machine learning. But we have a true model, which means that we are going to make a couple of assumptions. The main assumption, and that is also the assumption that usually gets most of the attention to us as econometricians, is that we are going to assume that u and x, they are going to be uncorrelated with each other, which means, of course, that this mean that we have over here is equal to 0. But you should realize that we make more assumptions than just that. The true model means more than that. And that is, of course, related to the model itself. This model itself, writing this model in this way, already makes a couple of different assumptions. The first thing, well, is pretty well known. And that is that at the moment that we're going to write this down, this is, of course, a linear model. And that means that we're going to assume that, well, x is going to have an impact on y, but the impact is going to be completely linearly. So this assumption that we have over here. Well, there are other assumptions that we actually make. An assumption which is not that important right now, but quite important for my own research, is that we essentially assume here that even though we have here an error term that we do not observe, we are going to assume that that error term comes to us in an additive way. We simply add it to this part that we have over here, which is essentially observed because of the fact that we do observe this xi over here. But we should realize that that is maybe not the most important assumption for us right now, but the most important assumption for the rest of the talk of today is that even we do assume that we know how this factor looks like. That is to say that we know exactly the, say, regressors in econometrics that we have to include. So that implies that the only thing that we still need to do is to estimate the beta coefficients, the unknown beta coefficients that correspond with respect to these regressors that we have over here. But that's a very important thing to realize. At the moment that we are econometricians, then all the, say, econometric analysis is assuming this true model. And it means that we are going to assume that we already know which x's should be included in this, say, factor that we have over here, which regressors should be included. And we should realize that all of the statistical inference is related to these assumptions that we have over here. So that means that unbiasedness, also the consistency, but even the standard errors that we usually report, and it doesn't really matter which kind of standard errors, whether these are the standard errors or the heteroscedasticity robust standard errors, or even the, say, clustered standard errors, they are going to be based on these assumptions that we have over here. But we should realize that even in an econometric context, we can always ask us the question, what is going to happen if this is going to be the true model and I'm going to exclude one of my regressors? Say I'm going to exclude this S regressor that we have over here. So this XS that we have over here, we're simply going to exclude it, where S could be, of course, equal to 1, 2, 3, 4, 5, etc. And the question arises, what is going to happen in that particular case? Well, it's very tempting for us as econometricians to think that at the moment that we're going to exclude a particular regressor, well, then at that moment in time, immediately this beta coefficient that we have over here is going to become inconsistent. Well, we should realize that that actually might be true, but we should also realize that this is not always going to be true. It's not always the case that at the moment that we're going to leave out the regressor, that then the beta coefficients automatically become inconsistent. We should realize that there are two particular restrictions that we need in order to have inconsistency of this beta at the moment that we're going to exclude a particular regressor. I'm pretty sure that you already know them, but I'm going to look at them another time. And that is, first of all, that beta S should be unequal to 0. Well, that's a very trivial one, because of the fact that if beta S is going to be equal to 0, of course, I can always leave out the XS that I have over here, because of the fact that then, even if this is going to be the true model, if I leave out the XS and beta S is exactly equal to 0, then I still have exactly the same model. Then leaving it in or leaving it out is exactly the same model. So if this is a true model, well, the left out XS with beta S equal to 0 is still exactly the true model. So therefore, we should realize that this is a very trivial one. But there is a less trivial one as well. And that is that apart from this restriction that we need, that beta S must be always unequal to 0, in addition to that, it should also be the case that the XS should be correlated with some of the other features that we still have in this XI that we have over here. That's very important to realize. At the moment that I'm going to have that this XS that we have over here is going to be completely uncorrelated to all of the other features, then even in the case that beta S is not equal to 0, then I can leave out my XS without actually risking that I'm going to get an inconsistent estimator. That's an important thing to realize. So therefore, we should realize that only if these two restrictions are going to be correct, so beta S should not be equal to 0, and XS should be correlated with some of the features that we have over here, then at that moment in time, we should actually not take out the XS that we have over here, because otherwise the beta coefficient is going to become inconsistent. But now a question that arises is, can we also say the other way around? That means that if any of these restrictions that we have over here is going to be untrue, should we then always take out these XS that we have over here? Well, that depends a bit on the situation. It first of all depends on the situation, whether you're interested in that particular beta coefficient. Typically, we're not. So then in that particular situation, the question arises, what should you do? Well, if you're not really interested in the beta S over here, then at the moment that we do assume it to be equal to 0, or we even know that it's going to be equal to 0, well, then it's always better to take it out. And the reason behind that is efficiency. We do not gain any consistency by leaving it in, but we do gain efficiency at the moment that we're going to leave it out. So then in that particular situation, it's always better to leave out the regressor that we have at hand. But what in the case that beta S is not equal to 0? and XS is going to be uncorrelated with all the other features. Well, then the situation is a little bit more difficult. And the reason behind that is because of the fact that then if I leave my XS out, what is going to happen then with respect to the variance that we've over here? Well, then you should realize that what I take out is in fact XS multiplied by beta S. And that of course has a variation. It actually explains this yi that we've over here. And that means, of course, that we should realize that that variation is going to get into the error term that we've over here. And if that variation is going to be very large, that is going to increase the variance that we have over here. And if that is going to be substantial, then even though we might take this excess out, which typically, of course, is going to give us higher efficiency, well, that might not always be the case at the moment that the variance of this thing is going to increase so much that in the end, we are going to lose, in fact, efficiency. So therefore, the question arises, how important in this case is, in fact, the variation of our XSI multiplied by beta S in the total variation that we have in this regress? If that's not too much, well, then it's better to leave it out. If that's very much, well, then at that moment in time, it is better to keep it. Well, as I already said, this is all about econometrics. And one thing we already know is that econometrics is all about the estimation of these beta coefficients that we have over here. That's the thing that we want to know a little bit more about. But you should realize that that's actually not the case at the moment that we're going to look at the present lecture series, and that's machine learning. In supervised machine learning, more in particular, we should realize that the only thing that really matters is the predictive power of a regression. So we're not that interested in this beta coefficients whatsoever. We're only interested in getting a regression that is going to give us a very good prediction of this yi that we've over here. Well, now you might say like, well, if we want to get a good predictor, then maybe the best thing always to do is to include as much as possible in this xi that we've over here. We do not know exactly what a true model is, but what we could do is include as much as possible in the x's. And at the moment that we even have continuously, well, x's over here, we have continuous features, well, then we might even include higher order terms. So apart from including x, we could also include x squared, x to the power 3, etc. That we could, of course, always do. And then we get a, say, regression with many, many different features. And then hopefully we are going to have a good predictor. Well, we do already know that that actually doesn't work also over here. And the reason behind that is because of the fact that what are we going to get at the moment that we're going to include a lot of x's? Well, we do already know that that actually means nothing else as that we're going to look at what I already called a couple of times before. Then we are going to have a complex model, a flexible model. We're going to get a model with many, many degrees of freedom, as we typically say in statistics. Well, these models, they usually have a very low bias, as we have already seen before. But we do also know that they typically have a very high variance. That's related, of course, to what we have said over here. So therefore, what we need to do, instead of just including as much as possible, is that we only should include those x's that are, in a sense, good enough in order to predict the y's that we have over here and balance the bias versus, of course, the variance, as we already have discussed before. Well, before we are going to look at that, we should realize that the famous R squared that we as econometricians use is actually not going to be so great over here. And the reason behind that is because of the fact that we do already know as econometricians that at the moment that we're going to include additional x's, then it's always the case that the R squared is going to increase. It doesn't really matter what kind of x we are going to include, but at the moment that we're going to include an additional regressor, an additional feature, then the R squared is always going to increase. It's even the case that at the moment that I ask a computer to, well, generate for me a completely randomly generated x, at the moment that I'm going to include that into my regression, then my R squared probably is not going to increase by a lot, but it's not going to decrease. and it might even increase a little bit. The question, of course, arises, why is that the case? Well, we should realize that the R squared in a regression context is one-to-one with the risk that we have looked at before. And it's one-to-one because of the fact that we are looking here at the training sample. What we're going to do is that we're going to estimate these beta coefficients, of course, with respect to the training sample. We should realize that it's one-to-one related to the so-called training risk. And that means that we do already know that the more x's I'm going to include over here, the smaller is going to be my training risk. And the larger, of course, is going to be my R squared. And that means that, like we have already seen before, looking at a training risk is not a good idea. It's also not a good idea to look at the R squared in order to say something about the performance, the predictive performance of a regression. The R squared only looks, at least at the moment that we're going to look at the R squared based on a training sample, only looks at how well we are able to fit the data. But we do already know that fitting data is not exactly the same as simply trying to get the best prediction. And actually, we already know what we have to do. What we have to do is, of course, not look at the training risk, but we should do cross-validation, or we should look at the so-called validation risk based on a validation sample. And that we can do here as well. What we could do is look at a large set of features, of course, less, like I already have said before. We might even want to include, say, higher order terms of the continuous features that we have over here. And then what we're going to do is that we're simply going to, well, estimate all kinds of different regressions. And then what we're going to do after we have done that is that we're going to choose that particular model that is going to give us essentially the best cross-validation risk, the lowest cross-validation risk, or the lowest validation risk at the moment that we're going to look at a validation sample. That actually works quite well, and you should say is also quite straightforward. Well, even though this works quite well and it's very straightforward, we should take into account that in practice, this is not going to be so useful. And the reason behind that can be explained at the moment that we're going to look at a very simple example. Suppose that the training sample has 1 million observations. And in addition to that, in addition to these 1 million observations, we're going to assume that we have only 50 potential features. We should, of course, realize that 1 million observations is quite a lot. These days, there are quite a lot of data sets that do actually have that many observations. If you think that that's a little bit too much, well, you can also think of exactly the same example, but with only, say, 100,000 or 10,000 observations. The most essential thing is actually, with respect to this example, the number of features that we have over here. Take into account that in big data, having 50 potential features, so 50 potential regresses that we have, it's even not that much in econometric data sets, but it's definitely not that much at the moment that we're going to look at big data. Take into account that, for example, in the Facebook example that we have looked at before, features are nothing else as pixels in a picture. And we should realize that even with the most simple smartphones these days, you can actually have more than 1 million pixels in a particular picture. So therefore, you should realize that actually 50 is a very low number of potential features. But the main question now arises, if we are going to do all the potential regressions with respect to these, say, features that we have over here, how many regressions do we have done? Well, in general, at the moment that we have p different features, you can show that the number of regressions that we can do is always equal to 2 to the power p, where p is then the number of potential features. That's not that difficult to understand, especially at the moment that we are going to look at just one particular feature. How many regressions can we do with one feature? Well, that is simple. We can either include that feature or not. And that means, of course, we can do 2 regressions with one feature. Now, of course, the question arises, how many can we do with, at the moment that we have 2 different features? Well, then it's going to be 4, because you should realize that then in that particular situation, we could include both features. we could exclude both of the features. We can include the first one and, well, exclude the second one. And we can do it the other way around. That means 4 different regressions. And more in general, what we can do is always include a particular feature or not. That gives us 2 different situations. And that means, of course, that we get 2 to the power different potential regressions at the moment that we have 50, say, p different features. Well, and then more in particular, at the moment that we have 50 different features, that means, of course, that we have roughly, well, actually a little bit more than 10 to the power 15 potential regression models. That's quite a lot, of course, but we should realize that after having run all these regressions, we are not there yet. Then we only know, say, the beta coefficients of all those different regressions, but we do not know which regression is going to be the best one in terms of predictive power. So then what we have to do is either have essentially a validation sample and calculate the validation risk, or what we have to do is that we could do a cross-validation. Well, let's do the last thing, and let's be very enthusiastic in this case. Let's do leave one out cross-validation. Well, that means then in that particular case that we are going to have 10 to the power 21 different regressions. 10 to the power 15 times 1,000,000 gives me this thing that we have over here. The question, of course, arises, how much time does it take to do 10 to the power 21 different regressions? Well, the answer to that is I have no idea. I have no idea, and it actually does, of course, depend on a lot of things. The computer that you're using, but also the software that you're using. Probably you shouldn't do this thing with Stata. Stata is actually, in that sense, quite slow. It would be better to use, say, directly, say, software that is going to be only fit for doing, well, regressions. Well, suppose that we are in a situation that we actually have that software, very professional software, that is going to be able to do very quickly regressions for us without doing anything else. And in addition to that, well, we should also realize that we have not just a computer at home, but maybe we have the best or one of the best, say, clusters that we have right now. Well, then it would be possible, of course, to do 1 billion regressions per second. I think that that is still quite challenging. Doing one regression, of course, even at your home computer, will not take you more than a second. But doing 1 billion at a time, that's still quite challenging, in my opinion. But the question then, of course, arises, if we can do 1 billion regressions per second, how much time do we have to take to wait until we actually have our final model? Well, that's 32,000 years. That's quite a lot of time, actually, to wait for one single result. So most likely I will be dead by that time. And in addition to that, that's maybe even quicker, the cluster that I'm using is also going to be dead by that time. So therefore, we should realize that we cannot wait for so long. So therefore, it might be very useful in this case to use an algorithm, to use a method that is automatically going to select a subset of our regressions that we have over there. What you should realize is that maybe we don't have to run all these regressions over here. Maybe there are methods, computer algorithms that can already see along the way that some of the regressions that we're going to have are going to be completely inferior in terms of their predictive power to other regressions that we have already looked at. Maybe we only have to do a very slight part of the total potential regressions that we have to do. Well, if we're going to look at something like that, then we are going to be in the world of regularization. Regularization means nothing else is that we are going to try to find a method that is going to help us to reduce the number of final regressions that we have to do. In order to understand the idea behind regularization, it's best to go back to the model that we have so far. Remember that we have yi at the left-hand side, we have xi beta plus ui at the right-hand side, and we have in total p different features. Well, what we have said so far, and that it was the main idea behind the previous slide, that it would be impossible to try to estimate all of the potential regression models that we have over here. But what we could do is that we could, first of all, ask ourselves the question, well, could we first just run all the potential regressions for a particular alpha that we have over here, where we are only going to allow to include into these axes that we have over here to include only alpha different regressions in this X that we have over here. Well, where alpha, of course, is going to be smaller or equal to p, and alpha could be equal to 1, 2, 3, 4, 5, etc. Well, before I go on, the first thing that I have to say with respect to that is that whatever alpha is, we typically know from econometrics that it doesn't make that much sense to run a regression without a constant. And therefore, within this alpha, we typically do not count the constant. So that means that if alpha is equal to 1, then we are going to have the constant plus one additional feature. We're going to do exactly the same with respect to p over here. So p equal to 50 means that we are going to have, in a sense, 51 different features, including a constant, and 50, of course, excluding that particular constant. So we will always consider a regression where we already have included a constant, even though I usually don't write it like that. Over here, we always include a constant in any kind of regression. Well, then what we can do is that for a given value of alpha being equal to 1, 2, 3, 4, or 5, or up till p that we have over here, we can then simply run all the potential regressions, which is of course less than all the potential regression that we have with respect to p. And then based on that, what we can do is that we can choose then that particular model that is going to give us the best predictive power. So that's either going to give us the lowest validation risk in a validation sample, or alternatively, we can look at the cross-validation risk at the moment that we're going to do cross-validation with respect to the training sample. And then what we can do is that we can start with a very low level of alpha. We can start with alpha being equal to 1. In the case that alpha is equal to 1, then we can do only p different regressions, because of the fact that then what we can do is that we can run a regression of y on the very first feature, we can run a regression of y on the second feature, etc. And then what we can do is, based on all these different regressions, we can, well, calculate either the validation risk or the cross-validation risk based on cross-validation as we do over here. And then we do know what is going to be our best predictor, conditional, of course, on the fact that alpha is equal to 1. Well, then we can go on. What we can do is that we can go on from alpha being equal to 1 to alpha being equal to 2. And then again, what we can do is that we can do all the potential regressions. This is now going to be a little bit more because of the fact that with alpha equal to 1, we can only do p regressions. With alpha equal to 2, we have potentially p times 1 minus p different regressions. But so we can do all those regressions, and then we can do exactly the same. We're going to either look at the validation risk or at the cross-validation risk, and we are going to choose the best performing model for alpha being equal to 2. Well, what we then can do is that we can compare the best performing model with alpha equal to 1 to alpha equal to 2. In general, if we go from alpha equal to 1 to alpha equal to 2, then we will see that the best performing model for alpha equal to 2 will give you actually a lower cross-validation risk. And that makes sense because of the fact that alpha being equal to 1 is, of course, a very restrictive model. So therefore, it's not very likely to give you the best, say, predictor. And alpha equal to 2, still quite restrictive, will generally give you better predictors. But then what we can do is that we can go on from alpha equal to 2 to alpha being equal to 3 to alpha equal to 4. And every time we are going to get the best predictors, and we are going to compare the different cross-validation risks with each other. But what you will generally see in that particular case is that, of course, the cross-validation risk will be the highest if alpha is equal to 1, It will go down at the moment that alpha becomes equal to 2, but it will probably even be smaller at the moment that alpha is equal to 3. But we will see at a particular moment in time that at the moment that we're going to increase alpha, that the cross-validation risk again is going to increase. Well, then we do already know, like what we have seen with respect to k nearest neighbors, that we already know the best predictor. We do already know then our best predictor because of the fact that at the moment that we're going to look at even higher alphas, well, then the best predictors for higher alphas will actually give us even higher cross-validation risk, which means that the best predictor is not there with respect to those really high levels of alpha. And that means that we already know which alpha is going to be the best, and we already have our best predictor. So that means that all those additional regressions that we would have done for higher levels of alpha, we don't have to do them anymore because we do already know what is going to be our best predictor. And that will reduce the number of regressions that we have to do, of course, considerably. But we should realize that this method that I just described is in machine learning usually called best subset selection. One great thing with respect to best subset selection is that among all the methods that we know of, it is going to give us always, say, the best performing predictor. It will give us the best performing predictor based on the fact that we can only include these features or not. Later on, we will see that we have even better predictors if we allow, well, a little bit more flexibility than that you just include a particular feature or not. But if you can only include a particular feature or not, as we usually do in regression models, then in that particular situation, best subset selection will always give you the best potential predictor. However, a bad thing with respect to best subset selection is that even though it might be a little bit faster than, say, the naive method of just, well, without any thinking, just running all the different, say, regressions, it is still going to be very computer intensive. And that is because of the fact that you should realize that we do not know beforehand how large alpha is going to be. And if alpha is going to be large, well, then at that moment in time, you still have to run a lot of regressions. Because the question arises, how many regressions do we have to run in every stage? Well, it's not that difficult to see that the number of combinations that we can have is actually equal to this thing that we have over here. And that means, of course, that at the moment that p is going to be equal to 50, and we are in the stage in which alpha is equal to 10, well, then you should realize that the number of regressions that we still have to make is going to be equal to 10 billion regressions. We don't know, of course, beforehand when we get to alpha equal to 10, because maybe after alpha equal to 5 or 6, we are already going to increase again with respect to our cross-validation risk, but we don't know that beforehand. It might be the case that we get to alpha is equal to 10 at a particular stage, and we do see that still, well, the cross-validation risk is not already increasing. Well, then we have to do all these 10 billion regressions, and even after that, we do not still know whether our cross-validation risk has been increasing. So in that sense, we are still going to do a lot of different regressions, and in that sense, we should still realize that best subset selection could be still infeasible. Now, of course, the question arises, can we look at alternative methods? Well, an alternative method is forward selection. Forward selection actually tries to be much faster by having, you could say, a memory. What we should realize is that at the moment that we're going to look at best subset selection, what does best subset selection do? Well, best subset selection, the only thing that it does is that for any alpha, it is going to calculate the best predictor. However, at the moment that we're going to go from one stage to the next, it's going to completely, you could say very naively, completely, well, forget about the things that we have done before. And you should realize that especially at the moment that alpha is still quite small, then typically we have, say, some very good predictors, some very good features that we will actually always include. Let's look at a very simple example. We have been looking before at house prices, and suppose that again we would like to, well, predict house prices. And here in this case, I really would like to predict house prices, not the house price per square meter or something like that, but I really would like to look at the house prices itself. Well, then at that moment in time, if I have, say, the size of the house in square feet, and it's not measured with error, what we have looked at before, well, then in that particular moment in time, that size in square feet will be a very good predictor, of course, of the house price. Because, well, how large a house is going to say a lot about the house price, of course. And that means that if alpha is equal to 1 in this, say, best subset selection, is going to be usually going to be, well, what is going to be selected is, of course, this size in square feet, because that is so important that it will actually outperform any other of the features that we have. Then at the moment that we're going to go from alpha equal to 1 to alpha equal to 2, it's going to be very likely to be the case that even in the case that alpha is equal to 2, that of course, this size in square feet, it's going to be included. Most likely with another feature, but you should realize that it's going to be included here as well. Well, you should realize that best subset selection doesn't take this into account. Best subset selection very naively is going to completely forget about what it has done before and is going to again look at all the potential regresses that we could actually include. Well, that is not what forward selection does. Forward selection actually is going to keep the, say, features that we already have included in our regression, and it's only going to ask which additional feature could we include in this case at the moment that we are going to increase alpha by 1 step. So it's only going to ask, well, given the fact that we have already included a certain set of features, which additional feature are we going to include at the moment that we are allowed to include one additional feature? Well, you should realize that, of course, forward selection is going to be much less computer intensive. To give you an example, what you should realize is that in the first stage, at alpha equal to 1, well, then we have exactly the same. Then, well, with respect to subset selection, we had p different regressions. And that's, of course, also the case if alpha is equal to 1 for forward selection. But then at the moment that we go to alpha is equal to 2, well, then we only have to do p minus 1 different regressions. We only have to look at, say, the additional, say, or the remaining features that we have. And we do already know that in best subset selection, it was equal to p multiplied by 1 minus p, or I'm sorry, p minus 1. So therefore, we should realize that at the moment that we're going to look at, well, forward selection is going to be much, much faster. And therefore, well, for any kind of reasonable data set, it is actually going to be feasible. But there is actually a drawback with respect to forward selection. And that is that you should realize that I just said that at the moment that we're going to look at best subset selection will always give you a result in such a way that we always will get the best performing model among all the potential models that we have. But that's not the case at the moment that we are going to look at forward selection. Forward selection will generally not give you the best performing model. And the reason why this is the case is because of the fact that what is very generally called in machine learning greediness. You should realize that forward selection only looks one, say, step ahead. It doesn't look a couple of steps ahead, and it also doesn't look backwards, or whether particular regressions that we have done in the past could actually be, well, not that great at the moment that alpha is going to increase. In that sense, you should realize that at the moment that alpha is going to be small, then at that moment in time, with forward selection, it may sometimes be the case that we're going to include a particular regressor. And then later on, we are going to include additional regressors. And suppose that we are going to now include 2 additional regressors that are going to be very much, well, correlated with the original regressor that we already included. Well, that means, of course, nothing else as that if we already know these 2 regressors that we have included, then this original regressor doesn't give us that much of information. And therefore, it may actually be better to leave it out if we have already included those other regressors. But that's not possible with forward selection. Best subset selection would actually do that, but with respect to forward selection, that is not possible because of the fact that you never take out a regressor that has already been included. And therefore, forward selection will usually give you less good results in the end than at the moment that we're going to look at best subset selection. But you should realize that the good thing, of course, with respect to forward selection is that it's going to be much faster. Well, another alternative method is going to be the case that we are not going to really look at the outcome variable, but instead we are going to look at the residuals. We are going to, at the particular stage, we are going to calculate the residuals based on the regression that we have done so far. And then what we're going to do is that we are going to try to fit the residuals. Trying to fit the residuals is, of course, in general the same as trying to get the best fitting model, because of the fact that the residuals are actually nothing else as a difference between what you're predicting and your outcomes. And therefore, you would like to get, of course, the residuals as small as possible. The good thing with fitting the residuals is that, of course, at the moment that you're going to fit the residuals, you cannot do that on, say, the regressions that you have already included. You can only do that on the, say, regressors that you're going to include. And that means, of course, that the only thing that you then have to do is to do one regression, say, at the time with respect to the residuals, with respect to just one regressor that we're going to have. And that means, of course, nothing else is that it's going to be much faster because of the fact that here in forward selection, you still have to include all the different regressors at the moment that you're going to do a particular regression. But with this one, it's just one regressor that you're going to have for any regression model. Well, this method is called forward stage-wise regression, and forward stage-wise regression is even faster than forward selection that we've over here. But also, again, we should realize that the drawback is that forward stage-wise regression, again, is going to be, well, essentially is going to give you a less performing model at the moment that we are done. So we get a quicker result, but the result by itself is going to be worse. Well, forward stage-wise regression, by the way, has some overlap with the idea of regression trees that we are going to discuss later. Now, an important question, of course, arises is which of these methods that we have discussed so far should we actually use? Should we use best subset selection, from which we do know that it's going to be very slow, but in the end, it will give us the best performing model? Or should we use forward selection or even forward stage-wise regression? Well, we do know that forward stage-wise regression is not going to give us the best model, but it's going to be much faster. But we should realize that in reality, or in fact in practical situations, we should not use any of these methods that I have discussed so far. And that is because of the fact that now we will actually look at regression methods that are going to be faster than best subset selection, or I'm sorry, they're going to be faster than forward stage-wise regression. And they are going to be better than best subset selection. So therefore, these kind of methods are going to be outperforming any of the methods that we have discussed so far. In order to understand the ideas behind these methods, it is best to go back one time more to best subset selection. Remember that best subset selection means that given a particular alpha, we are going to, well, run all those potential regressions based on the potential features that we have. We are going to run all those potential regressions that have exactly alpha features included. Well, what we can do is that we can do this. We can simply do all the potential regressions, but we can also write this down as a minimization problem. Then we get, mathematically at least, this minimization problem that I have written down over here. What we're going to do is that we're going to minimize the sum of squared residuals, take into account that the way I've written it down over here is going to be a little bit different from what we looked at before, because of the fact that what we did before was that we said that we have a potential set of features. And then among those features, we have to include those axes in our regression that are going to be used as features. So not just as potential features, but really as features in the regression analysis. But here what we're going to do is that we're going to include all the potential, say, P features that we are going to use for the prediction of the y that we have over here. So we're not going to here only look at those features that are finally going to be included in our final model, but here we are going to include all the different features. Well, this means, of course, that if we're going to minimize this thing that we're over here, is that we simply are going to get usually the beta coefficients that are going to be exactly equal to ordinary squared based on those P different features that we are going to have. But that's not what we're going to have over here because of the fact that we are still going to have this restriction over here. And that restriction says that the number of beta coefficients that are going to be unequal to 0 should be smaller or equal to alpha. Because of the fact that what I do over here is that I sum here over all the different features. And what I'm going to do is that I'm going to count here the number of, say, features that have a beta coefficient, which is going to be different from 0. And now what I'm going to say is that the, say, number of beta coefficients that cannot be equal to 0 cannot be larger than this alpha that we have over here. Well, that is exactly the same as what we in fact do at the moment that we are looking at best subset selection. Then for any states alpha, we are going to look at those regressions for which, in fact, well, there are going to be alpha beta coefficients which are not going to be equal to 0. This is just another way of looking at this. What we could do is that we could include, say, only alpha regresses over here. But what we could have done as well is that we could simply look at, well, all the different axes. So the P potential regresses that we could have, the P features that we have, but we are going to already set, well, a number of them already exactly equal to 0. And what we say over here is that for any regression that we're going to look at over here, we cannot set more than, say, alpha regresses in such a way that the coefficients are going to be, well, different from 0. Well, this is exactly the same thing that we are going to have at the moment that we're going to look at best subset selection. Is this going to be helpful? Well, theoretically, maybe yes, but practically not that much because of the fact that there is no way I would be able to minimize this other than the way that I already talked about before. That is to say that, well, what I have to do is that I have to run all the different regressions that we could actually have in such a way that, say, exactly alpha of the beta coefficients that we have over here are going to be unequal to 0. So that means just including all the potential regressions for which we have alpha different regresses over here. And well, then I'm going to choose the one that is actually going to give me the lowest thing over here. But looking at it in this way is actually quite nice, even though, well, practically it's not going to help us that much. The nice thing with respect to this is that this is actually saying that what we do is that we minimize the sum of squared residual of the full model that we have over here with all the P potential regresses, all the features included. And we are going to have a restriction with respect to these betas, which is a restriction that we usually call an L0 norm. This, what we have here at the left-hand side, is usually called the so-called L0 norm. Strangely enough, especially for US mathematicians, you should realize that this is not actually a norm. It doesn't fulfill all the criteria with respect to a norm, but still it's called a norm because of the fact that this is usually called an L0 norm. That means nothing else is that best subset selection is actually a method that minimizes the sum of squared residuals under this restriction that we have over here that has this L0 norm. Now we should realize that we don't have to restrict ourselves to an L0 norm. We could do exactly the same, but use another kind of norm. What we could, for example, do is that we could look at the so-called L2 norm. What does that mean? Well, that means that we still are going to minimize the sum of squared residuals of all the potential features that we could actually include. But now we're going to have the restriction that, well, remember that we already looked at the L2 norm before because of the fact that when we were looking at the loss function, then I already introduced the L2 norm. And that was actually nothing else than the quadratic loss function. And that means that in this case, an L2 norm means that we are not going to look at the number of betas that are going to be equal to 0. But now what we're going to do is that we're going to sum over all the betas and we actually take their squares. This thing that we have over here is going to be now our left-hand side of the restriction that we have, a so-called L2 norm. But the right-hand side is exactly the same. We still have this alpha that we have over here for some alpha which is going to be positive. Well, if we're going to use this L2 norm, then we get another famous regression model because of the fact that this is usually called rich regression. However, the idea behind rich regression and best subset selection is exactly the same. What we are generally going to do in best subset selection is that best subset selection is going to look through this minimization problem that we have over here, is going to look at those x's that have a good predictive power with respect to this y that we have over here. And those x's that do have a good predictive power, well, they will actually get a beta coefficient that we have over here, well, which is going to be different from 0. They are, of course, going to be exactly the same as the ordinary squares beta coefficients that we're going to get from the restricted model, where we exclude these x's over here, for which the betas are exactly equal to 0. So in that sense, well, you should realize that what best subset selection does is that it's going to look at those, say, x's which have a good predictive performance. Well, that is exactly the same what you would actually get at the moment that you're going to look at this minimization problem that you have over here. The moment that you are going to look at rich regression, then again, for those, say, x's that have a good predictive performance, we're going to set the beta coefficients, well, at least close to those that you would have had at the moment that you're going to run the ordinary squares. It doesn't have to be exactly the same, but you should realize that for those, say, x's that have a good predictive performance, you allow for the beta coefficients to be relatively large because of the fact that you would like to predict with those particular, say, features that can predict so well. Well, that, of course, is not going to be a problem with respect to this because of the fact that you want to have them really large. But now suppose that you're going to have an x which hasn't such a good, say, performance in terms of predicting this yi very well. Well, for those betas, what you're going to do is that you, well, don't want to set them too large. And the reason behind them is because of the fact that they do not perform so well. And in addition to that, they actually are going to have a big impact on this, say, sum that we have over here if we set them too large. So therefore, what we will not do with respect to these ones is that we will not try to set them exactly equal to their ordinary squares coefficients, because of the fact that that would actually result in the fact that this restriction is not going to hold. And that means, of course, that rich regression does more or less the same as what we had with respect to best subset selection. It is going to, well, look at those x's that have a good performance in terms of predicting this thing over here. For those, the beta coefficients are going to be set, well, more or less the same as with respect to ordinary squares. And with those x's that do not have such a great performance in terms of trying to predict this y over here, the beta coefficients will be set very, very low. Probably not equal to 0. That's not necessary because of the fact that if I have here a very low level of this beta coefficient that we have over here, I square it, and it becomes even smaller. But what you should realize is that you get things which are quite comparable to this thing that we have over here. But then, of course, the main question arises, why would you actually want to do this? Well, we will later on see that there is a good reason to do this. Generally, doing this over here will actually get you a better predicting performance than what you are going to get at the moment that you're going to use best subset selection. But there is another reason why you actually would like to do this. And that has all to do with the fact that this is going to be much faster. This is going to be much faster than what you would have had at the moment that you would have done best subset selection. We do know that best subset selection actually is not that fast at all, but ridge regression is going to be extremely fast. And the reason behind that is because of the fact that, unlike what we had in the previous slide, this thing that we have over here actually does have a solution. We can immediately solve this thing that we have over here, and we will see that the solution is actually not that much more difficult than a standard regression model. How can we do that? Well, that we can actually do by looking at a method that you already know of, and that is Lagrange multipliers. We do already know what Lagrange multipliers are because of the fact that we do know that generally can use Lagrange multipliers for situations in which we would like to minimize under a particular constraint. Well, now you have to take into account that that constraint usually has to be an equality constraint rather than the inequality constraint that we have over here. But you should take into account that even though we have here an inequality constraint, it is not very likely that we are going to have here an interior solution. At least at the moment that alpha is not going to be too large. At the moment that alpha is going to be very, very large, well, then at that moment in time, we will generally, of course, see that we are going to have simply the ordinary squares outcomes because, well, it could, of course, be possible that even the ordinary squares outcomes of running the, well, unrestricted model is still going to, well, obey this rule that we've over here at the moment that alpha is going to be extremely large. Well, then at that moment in time, alpha is not going to be important at all, and we are going to get an interior solution. But as long as alpha is going to be relatively small, then of course, what we're going to do is that we are not going to get exactly the ordinary squares solution of the unrestricted model, but we have then to reduce some of the betas. Well, we don't want to really reduce them too much, but we have to reduce them in order to obey this restriction that we've over here. But we should realize that as long as we can still increase some of the betas towards the values that we would have had in the case of ordinary squares, then we would always like to do that. Then we can always minimize this, say, or reduce this criterion function even further. And that means that in general, at the moment that alpha is not going to be too large, we will always be on a boundary solution. And that is the reason why we will actually be able to lose Lagrangian as long as alpha is not too large. Well, then at that moment in time, we can change this inequality restriction that we have over here into an equality restriction. Well, that means, of course, that we can simply look at our Lagrange function that is usually denoted here by this L, this calligraphic L that we've over here, and that is going to be a function of beta, the beta, of course, that we already had over there. It is p-dimensional, and in addition to that, we have this scalar lambda that is over here, which is usually called the Lagrange multiplier. Well, how are we going to write this function over here? The idea usually is that we're going to minimize this function over here without any restriction, rather than trying to minimize this thing over here with respect to that, say, restriction that we have over there. Well, the Lagrange function is always equal to, well, first of all, this function that we have over here. In matrix notation, that looks like this thing over here. And then in addition to that, we are going to have, well, always minus lambda multiplied by the restriction that we have over here, but we have to write it in such a way that we have at the right hand side 0. Well, what I'm going to do is that I'm going to bring this to the other side, and we get alpha minus, well, the sum of the beta I squareds. That's of course equal to beta t times beta. So therefore we're going to get minus lambda multiplied by alpha minus beta t times beta that we have over here. And then the only thing that I actually have to do now is that I have to minimize this Lagrange function that we have over here with respect to beta and lambda. That means, of course, that I'm going to have to write down the first order conditions. Well, that's not that difficult. Then the first thing we need to do is that we have to look at the first order derivative with respect to beta. Well, let's first look at this part over here. This is always a bit difficult because of the fact that this is with respect to matrix notation. But that means actually nothing else as trying to minimize or to take the first order derivative with respect to this function that we have over here with respect to beta. Well, that's not that difficult. Then we get the 2, and of course, in front. We get yi minus xi beta multiplied by minus xi, of course. So we get in total, we get minus 2 times xi multiplied by this thing that we have over here. In matrix notation, that's nothing else as this part that we have over here. But we still have to also take the first order derivative of this thing that we have over here with respect to beta. Well, that will give me minus lambda multiplied by the first order derivative of beta t times beta. Well, that's actually nothing else as minus beta. So I get in total, I get 2 times lambda times beta. Well, this is actually nothing else as, of course, the first order derivative is equal to 2 times beta, of course, because of the fact that it's going to be the first order derivative of this thing that we have over here. So we get 2 times beta. So therefore, in total, what I'm going to get are all these things over here. I have to set it equal to 0. So therefore, this is now going to be my first order condition. I can divide the left and the right hand side by minus 2 in order to get the next step that we have over here. Well, then what I can do as well is that I can now look at the, say, first order derivative of our Lagrangian with respect to lambda. Well, that in general is very simple. Then what we're going to get is simply this part that we have over here. And well, that will actually give us this equation that we have over here. Well, now what I would like to do is that I have to solve, of course, these two functions, or these two equations that we have over here with respect to lambda and beta. How can I do that? Well, my strategy now is going to be that I first would like to write from this equation that we have over here, I would like to write beta in terms of lambda. Then I can actually substitute it into here. And then, well, I will get actually a particular, or will be able to solve lambda then in terms of everything else, and substitute that then back in the equation that I had with respect to beta. And then I actually also have a solution of beta. Take into account, by the way, that we're not really interested in this lambda that we have over here. The only reason why we include it over here is because of the fact that we need that for the Lagrangian. But in the end, it is not going to be of any value for us. Well, now what we can do is that we can rewrite this first order condition. I just have written it here another way around. And then what I'm going to do first is that I'm going to, well, get rid of here of the parentheses. So then I get xty, well, minus xtx times beta. So in total, what I'm going to get is this thing over here. Now I multiply 2 times by beta. So what I can do is that I can take this beta out of the parentheses. Then I get xtx plus lambda times beta, of course. But you should realize that that is not allowed because of the fact that then I'm going to add up a matrix with a scalar. So what I have to do first is that I have to make this, say, scalar that I have over here also a matrix. And the way I'm going to do that is that I have to multiply it by the identity matrix. So therefore we get here xtx plus lambda times the identity matrix, which is going to be the same dimension of this thing over here, so p by p. And then that is going to be multiplied by beta. Well, I will take that thing immediately to the right-hand side. So therefore, in total, we're going to get this thing over here. And then the only thing that I still have to do in order to get a, say, formula with respect to beta is that I have to now, well, multiply the left and the right-hand side by the inverse of this matrix that we have over here. In a scalar case, this would be just dividing by this thing that we have over here, but that's not allowed with respect to matrices. So therefore, what we need to do is that we have to multiply the left and the right-hand side by the inverse of this thing that we have over here. What do we get then? Well, then we simply get this relationship that we have over here. Well, this looks like a very nice relationship. Before I'm actually going to go on at all, this looks like a very nice relationship. It is equal to xtx plus lambda I inverse multiplied by xty. Well, anyone who has ever seen the solution with respect to ordinary squares before would immediately say, like, well, this is almost like the solution that we have with respect to ordinary squares. We have with respect to ordinary squares is that we always have xtx inverse multiplied by xty. So more in particular, if lambda would have been exactly equal to 0, then we simply get the ordinary squares result over here. Well, generally lambda will not be equal to 0. We will see in the next slide that lambda generally will be equal to something which is positive. And therefore, we are going to get, well, something that looks, of course, a lot like the ordinary squares, but we are going to get an additional term here over here. Now, an important question that arises is this thing that we have over here, we have to invert it. Is this thing by itself invertible? Well, what we should realize is, of course, that we know already from standard linear regression that this thing that we have over here, xt times x, that should be invertible in order to do at all the regression. If this thing is not invertible, then we can actually not do our regression. So this thing can be considered, at least in our case, hopefully to be invertible, at least in a standard regression framework. So then the question arises, is that this thing that we have over here invertible? Well, you should realize that at the moment that I'm going to add a positive constant along the diagonal matrix that we have over here, which is definitely going to be positive as well because of the fact that we get there the square terms, well, then we are going to make actually, well, then that will not make our, say, matrix uninvertible. It will not make it singular. We can even say it a little bit more. We might even say that even in the case that this xtx is going to be singular, then in that particular moment in time, if I add along the diagonal matrix, I add a positive lambda over here, then it might even become actually non-singular, invertible. So that means that if xtx is invertible, well, then this thing is going to be invertible as well. But we can even say the other way around. If xtx is not invertible, which means in econometrics, of course, that we have perfect multicollinearity, well, then at that moment in time, it could still be possible that this whole thing over here is invertible. So that means that then still beta could actually be calculated. Well, that is important to realize because of the fact that why could we actually have perfect multicollinearity in this case? Well, among other situations, you should realize that that is always going to be true at the moment that the number of observations that we have is less than the number of regressions that we have. If we have more regressions than observations, then this thing is always going to be singular. But we should realize that if lambda is large enough, then at that moment in time, then this thing can still be calculated, even in the case that we have more regresses than observations. And that means that in ridge regression, we can have a situation in which the number of observations is more than, or actually less than the number of regresses. So the number of regresses is more than the number of observations. But that brings me back to the question, how are we going to now solve for this lambda? How large is lambda? Well, that we can do by substituting this right-hand side into there, and then we get this thing that we have over here. Well, this is a little bit of a disappointment because of the fact that now we're going to see that this is, first of all, very difficult. And we can immediately see over here that there is no, say, closed form solution of lambda in terms of everything else. We have here alpha at the left-hand side and lambda among many other things at the right-hand side. Well, it is going to be impossible for me to rewrite this in such a way that I have lambda at the left-hand side and everything else at the right-hand side. That's actually what I wanted. But we should realize that this, of course, can still be done numerically if I actually want to do that. In addition to that, I see one additional thing, and that is that even though the relationship is complicated, there is a negative relationship between alpha and lambda. That's not that difficult to see because of the fact that lambda is here in what we could call the denominator. And that means, of course, that at the moment I'm going to increase alpha, well, from a particular situation, then I have to, of course, decrease this lambda that we have over here in order to make these two things equal to each other. So that means that there is a negative relationship between lambda and alpha, and it is monotonic. And that's actually quite fortunate, because we should realize that even though we try to calculate here lambda, and even though I said, of course, that I'm not really interested in lambda, I only want it because of the fact that I would like to calculate this beta, you should also realize that I'm actually not that interested in alpha. And the reason behind that is because of the fact that alpha, unlike what we had with respect to best selection, it doesn't really have a good interpretation. And therefore, why would we then be interested so much in setting, first of all, alpha and then calculating lambda, if alpha by itself doesn't have any interpretation? The only thing that we actually want to do in the end, of course, is to set alpha in such a way that we are going to, well, get the best predictor, like what we actually did with respect to best selection. But that means that I'm not really that interested in this alpha in the first place. So therefore, what I could do instead is, instead of first setting an alpha and then calculating lambda, I could just also simply set a lambda in the first place. And that's actually what you do in ridge regression. So in ridge regression, instead of first setting an alpha and then trying to calculate the corresponding lambda, and then substitute that into this equation that we've over here, we simply are going to set lambda. Well, there is, of course, a corresponding alpha that we can relatively simply calculate, but since we are not as interested in this alpha whatsoever, we simply are going to do this thing over here. And that's exactly what you do at the moment that you're going to do a ridge regression in either R and Python. The only thing which is not that nice with respect to R and Python is that R and Python actually ask you to set an alpha. Now you might say, like, well, that means that you still have to set this thing over here. But that's actually not true. And that's because of the fact that even though actually every book, every statistics book actually calls this thing that we have over here lambda, and that thing that we had before, alpha, you should realize that the alpha that you have to set in Python and in R is actually the lambda that we have over here. So therefore, what we do in Python is that we actually set alpha, but unfortunately in Python it is called alpha. Well, and now the question arises, how do we get now the optimal value of this lambda that we have over here? How do we get the best predictor in the end in order to choose this lambda that we have over here? Well, the general answer to that particular question is, of course, cross-validation. But how are we going to do that in practice? Well, what we typically do in practice is that we're going to start with a very high level of lambda. What does that mean? Well, that means, of course, that we have a very small value of alpha. What does that mean in terms of ridge regression? Well, that means that we are, of course, in a very restrictive way. If alpha is going to be very, very small, in the end, if alpha is going to be close to 0, well, then all the betas that we have over here must be very close to 0. And that means, of course, that we essentially are going to run a regression of y and a constant. Well, that will generally, of course, not give us the best, say, cross-validation. It will not give us the best cross-validation risk. But what we should take into account is that what we in the end want to get is that we then would like to reduce the values of lambda. How are we going to do that? Well, we typically do that by reducing the value of lambda, say, every time by about 10%. So we reduce it, for example, at the moment that we start with, for example, lambda equal to 10, then we are going to reduce it to, for example, lambda equal to 9, for example. And then we are going to recalculate it. If you think that that's too crude, then we can also reduce it by only 1% or 5%. Doesn't matter that much. But what we're going to do is that we're going to reduce the time. And then we will see that, first of all, the cross-validation risk will actually drop quite quickly, as we have also seen with respect to best subset selection. And then at a particular moment in time, it's going to increase again. Well, then we should realize that then again, we are already past the optimal value. And then we can simply go back. Then we already know which lambda we have to choose. And then we get our optimal predictor. I would like now to go on with the next method, and that is the method of the lasso. What we have seen at the previous slide is that RICH is actually a very good method. We have seen that RICH is much faster than best subset selection, and we can even say that RICH is going to generally perform also quite a lot better than best subset selection. And therefore you could actually say that RICH regression has been one of the most important breakthroughs with respect to machine learning. Now the question of course arises, given the fact that RICH is so great, is it also often applied? Well, the answer to that is actually no. And the reason behind that is because of the fact that most people actually don't use RICH, but they use the alternative, and that is the lasso. Most articles that I have been reading, especially in terms of applied econometrics, well, most of the people actually don't use RICH, but they use this method that we've over here, the lasso. And the question arises, what is the difference between the lasso and RICH? Well, that is now very simple. Instead of using an L2 norm, as we have seen with respect to RICH regression, the lasso uses an L1 norm. So that means that, again, what we're going to do is that we're going to minimize the sum of squared residuals, as I have it over here. But now, at this moment in time, we're not going to take the sum over the beta I squared, but we are going to take the sum of the absolute values with respect to beta I. But the idea, of course, is exactly the same. What we need to do is that we are not allowed to set our betas too large, because of the fact that then otherwise we are not going to obey this particular restriction that we have over here. Again, we have here an alpha. And again, of course, this alpha that we have over here is going to be, well, restricting this thing that we have over here. Again, alpha is going to be larger than 0. But by the way, take into account that alpha here also doesn't have any interpretation. But we can even say that the alpha that we have over here is unrelated to the alpha that we had with respect to RICH regression. That is to say that at the moment that we have a particularly good alpha for, say, RICH regression, then we cannot use that for the lasso. Well, what I can say about the lasso is that unlike with respect to RICH regression, we cannot directly solve this system that we have over here. That is to say that there is no closed form solution with respect to this system, this minimization problem that we have over here. But still, it is relatively simple using linear programming techniques in order to get the beta coefficients that we have over here. The reason why you can actually not directly solve this has to do with the fact that this function that we have over here, these absolute values, they are not differentiable at 0. So therefore you cannot use, for example, Lagrange multipliers. Still, even though we're not going to use Lagrange multipliers, there is a lambda over here. And the lambda actually has more or less the same interpretation as the lambda that we had with respect to RICH regression. That is to say that, first of all, there is a negative relationship between alpha and lambda. That is to say, well, low values of alpha correspond with high values of lambda that we have over here. And in addition to that, we can also say that in Python or in R, what we actually do is that we set this lambda rather than that alpha that we have over there. But otherwise, we can say exactly the same things as with respect to RICH regressions, the things that I already have said before. But what I would like to do now is that I would like to make a comparison between the lasso and RICH. In which cases should you use the lasso, and in which cases you should use RICH. But before I'm going to do that, I would like to very quickly discuss an alternative idea behind regularization. Well, the way I have presented regularization right now, I do think that that's a very nice way. In my opinion, it is at least very intuitive to start with best subset selection, say that best subset selection is actually a way in which we are going to minimize something with respect to restriction. And then what I said, like, well, we can also replace that particular kind of restriction with other restrictions. Instead of using an L0 norm, we can use an L1 norm as in the lasso, or an L2 norm as in rich regression. But we should realize that in most books, it is not presented like that. In most books, what we do is that we are going to formulate regularization as actually a result of a penalized loss function, minimizing a so-called penalized loss function. Therefore, we need a penalty function. The penalty function that I'm going to introduce over here is denoted by this nu that we have over here, and nu is going to be a function of beta. And what you should realize that for any choice of beta that we're going to have over here, we're going to receive a, say, non-negative penalty. So we can expect that for some betas that we have over here, we're going to get another penalty than for other betas. And then what we're going to do is that we're going to minimize this, well, criterion function that we have over here, that I denote here by capital lambda. And capital lambda is, first of all, the sum of squared residuals. So that means that if we would simply minimize this thing that we have over here, then of course we are going to get the ordinary squares estimators for all the different features that we have, but we add to that our loss function. And that means that even though, well, generally, if you would like to minimize this thing over here, you would choose the beta coefficients exactly equal to ordinary squares, but you're not going to do that because of the fact that sometimes you might be, well, penalized quite a lot. It's typically the case that you're going to be penalized a lot at the moment that you're going to set the beta coefficients exactly equal to the ordinary squares. And therefore, you're going to get another result. Now, the question, of course, arises, what penalty function are we going to use? Well, at the moment that nu beta is going to be equal to lambda times beta t, beta transpose times beta, well, then what we have over here, well, is actually nothing else as an L2 norm. And then the solution with respect to minimizing this thing that we have over here is going to be rich regression. Well, if we instead, what we're going to do is that we're going to choose for this nu beta that we have over here, the L1 norm, well, then at that moment in time, we are going to see that we are going to have the lasso. Then we are going to get exactly the results that we have with respect to the lasso. So therefore, we can say that both rich regression and the lasso are special cases for this minimization problem that we have over here. Of course, we could also have used other kind of penalty functions. Then we get other kinds of regularization algorithms. One thing that you could do, and that's actually also possible to do that in Python, is that you're actually going to look at a combination of the two. So you're, for example, going to have, well, lambda 1 times beta t beta plus lambda 2 times this thing that we have over here. And you get something which is going to be some kind of in between rich regression and the lasso. Even though that might be interesting to do, I'm not going to discuss that over here. What I would like to do is that I would like now to say some words about the, say, choice between the lasso and rich. When should you use which kind of method? When should you use rich regression? And when should you use the lasso? Well, one thing that I can immediately say is that at the moment that you're going to look at the lasso, because of the fact that lasso doesn't have an explicit form solution, we have to do it with respect to linear programming techniques. Well, I'm not a numerical mathematician myself, but I do know that the lasso is going to be much slower than rich regression. Whether that's really a problem depends nowadays a bit, of course, on your computer power and maybe also on your patience. But you should realize that even nowadays, even though you should realize that the lasso is always pre-programmed in Python or in R, even in Stata, it's now very easy to do the lasso. That will be quite quick, but you should still realize, and I do not know exactly how much faster rich is going to be, but I would not be surprised if somebody is going to tell me that ridge regression is going to be at least 10 times as fast as the lasso. That, of course, doesn't mean that you have to wait days or maybe even years in order to get a reasonable result from the lasso. Also, lasso nowadays goes pretty fast. So if you can wait for that, then there is no problem at all. But at the moment that you have a big data set, a really big data set with many, many observations, many features, and time is then your issue, well, then it might be good to consider ridge regression rather than the lasso. Another good thing to say about ridge regression is that, at least in my experience, ridge regression typically tends to perform better than the lasso. And that's, of course, important because of the fact that we do know that performance, predictive performance, is very important in machine learning. Now, of course, the question arises, why is that the case? Well, that has something to do with the choice of this L2 norm that we have over here. This L2 norm is actually very fortunate because of the fact that it's very flexible. Using this L2 norm, you should realize that ridge is able to, in fact, well, categorize or, in fact, classify the different kind of regressors, or maybe better to say features that we have over here. At the moment that we're going to look at ridge regression, then the very good performers, so the very good predictors, as I already said, well, they will generally be set close to the ordinary squares values that we would have had over here if we would have simply done ordinary squares with respect to this regression that we have over here. So that is, well, typically the same as in best subset selection, and also it's the same as in lasso. But you should realize that at the moment that we have, say, situations in which this xi is not such a good predictor, well, then generally what ridge will do is that it will set the beta coefficients actually quite low. It will generally not set it exactly equal to 0. And the reason behind that is because of the fact that if I, for example, have a beta coefficient that is equal to 0.01, well, then at that moment in time, if I'm going to square it, it becomes equal to 0.0001. So therefore, it doesn't contribute a lot on this left-hand side that we've over here. So why not just set it then still a little bit positive? It doesn't have to be exactly equal to 0. In addition to that, we can also look at, say, features that are a little bit in between. They're not extremely good, say, predictors, but they're not extremely bad either. They have some contribution to the prediction. Well, what you will generally see is that for those predictors, ridge will do something in between as well. It will simply, well, set these beta coefficients not close to their ordinary squares, but it will set it somewhere in between. It will not be high, but it will not be very close to 0 either. And that means that, well, with respect to this very, well, flexible form that we've over here, ridge regression can categorize the different features that we have over here with respect to their predictive power, with their relative predictive power that they have, of course, that they contribute to the final prediction that we have over here. And that makes usually ridge regression to perform better than the lasso. And the reason behind that is because of the fact that you should realize that, of course, the lasso can do something like that as well. But the problem with respect to lasso is that you do not have here beta I squared, but you have beta I in absolute values. And that means, of course, that at the moment that you have not such a great predictor, then at that moment in time, well, then you will generally see that actually, well, the only thing that the lasso can do in order to have a very small contribution with respect to this thing that we have over here is to simply set it equal to 0. And that is what you typically are going to see. So unlike what you have seen with respect to ridge regression, at the moment that we're going to look at lasso, at the moment that this alpha is not too large, of course, then the lasso will typically set many, many of the betas that we have over here exactly equal to 0. So in that sense, it looks a lot like best subset selection. And therefore also you do see that the performance of the lasso usually is not as good as with ridge regression. But the question now arises, of course, I have just said that, well, most people actually don't use ridge, but instead they use the lasso. And now I have actually said only good things with respect to rich and nothing good with respect to the lasso. You should realize that the differences, of course, in the end, with respect to the lasso and rich, are not that large. So there could be a couple of reasons why lasso still is used so often compared to rich. The first reason might be simple. It is pre-programmed, for example, in Stata, and it's not, well, rich at this moment in time is, at least as far as I know, not pre-programmed in Stata. Maybe a lot of people have heard about lasso much more before, so therefore they they have seen other people doing it, and therefore they actually use the lasso instead of rich. I think that these are all very good reasons to use the lasso over rich regression, but you should realize that that might not be the most important reason why people will actually prefer the lasso over rich. The most important reason, I think, why people do prefer the lasso over rich is because of the fact that, well, actually exactly the things that I said right now. Because of the fact that the lasso usually sets a lot of things equal to 0, that makes it maybe also a little bit more interpretable. You should realize that at the moment that I have, for example, an application in which I have 500 different features, that is not too much, of course, that at the moment that I'm going to use the rich regression, rich will set all the beta coefficients that we have not equal to 0. There will be very few beta coefficients that will be set very, very close to 0, such that we can say like, well, they are exactly equal to 0. But none of them will be exactly set equal to 0, and many of them, they will be more or less small, but it's a little bit difficult to say whether they are set small because of the fact that they're really bad predictors, or whether they are set small because of the fact that even their ordinary squares coefficients would have been quite small. And they might actually be that, in that case, very good predictors, but they just need a very small level of beta. That is different in the lasso, because at the moment that I'm going to have the lasso and I have 500 different potential regressors, so 500 different features, if I'm going to put them in over here, well, then it is not that uncommon that the lasso is going to set 480 or 470 of them exactly equal to 0. It depends, of course, a bit on this alpha that I have over here, but if alpha is going to be small, then most of the, or almost all of the beta coefficients will be set exactly equal to 0, and only, say, remaining 20 or 30 beta coefficients are going to be set not equal to 0. And that makes it, of course, much easier to interpret it, because then you should realize that then you could, as a researcher, just look at all those different, say, features that are having beta coefficients not equal to 0. And then you could say like, well, these are the, say, features that are important for predicting. Well, that is, of course, correct. But you should realize that you should also be a little bit cautious with using this reason for preferring the lasso over rich regression. I can come up with at least 2 reasons why you should actually be a little bit cautious of here. The first reason is that you should realize that in general, machine learning is not made for interpretation. You should realize that the reason why we use machine learning is because of the fact that we would like to make good predictions. That's what I already said at my very first slides. And therefore you should realize that there was no interpretation in that goal, in that main goal of supervised machine learning. There's also a reason why machine learning is, of course, called machine learning and not human learning or something like that. It's the machine that is going to make the predictions. And for a machine, a computer, it really doesn't matter that much whether the, say, method that it's using is very good to interpret. But there is actually even another reason why you should be cautious over here, because you should realize that interpretations can be in machine learning, especially with respect to the lasso, can be extremely dangerous. And that actually brings me back to one of the first examples that I looked at. Remember this example where I said that I would like to look at house prices. I would like to predict house prices. And I said that suppose that we are in a situation in which we have a model, or actually in which it's going to be true, the true model is in such a way that the house prices are only determined by the location of the house as well as the size in square feet. But in that particular example, I also said that, well, the size in square feet as we measure it is highly measured with error. And in addition to that, I also said that the number of rooms that we also observe is not measured with error, and that there is a very clear relationship between, say, the size of the house and the number of rooms. And remember that I said at that moment in time that at the moment that you're going to do machine learning, well, then the best thing to do is to include, say, the number of rooms into a regression of the house prices. And most likely, for example, at the moment that you would have done the lasso would actually do that as well. And it would generally drop, of course, the size in square feet, simply because of the fact that we can already use the, say, number of rooms as a measure for the size in square feet. But then interpreting it is going to be very, very dangerous, because of the fact that we do already know that the number of rooms in a particular house is not going to have an impact on the house price. It's only used for, well, doing a good prediction, but it's not that at the moment that I'm going to increase the number of rooms in a house, that is going to increase the house price. So you should realize that making interpretations should be done very cautiously in general. They can be dangerous because of the fact that you would make actually the wrong, say, conclusions based on that. So therefore, once again, well, there is no problem to use the lasso, in my opinion. But don't I would say generally, don't use it only because of the fact that you think it is better for interpretation. Now, I would like to finally say something about the relationship, well, something which is actually related to both Rich and the lasso. And that is that Rich and the lasso are both subject to the sizing of the features. In order to explain that, let's go back to this slide that we have over here, but it's actually also true for Rich, but this is of course the slide with respect to lasso. Suppose that we again would like to look at house prices, and suppose that in this particular case, we are going to include here the size in square feet. But at a particular moment in time, I realized, well, I'm looking here at European data, and therefore I don't have the size in square feet, but instead I'm going to use the size in square meters. The question, of course, arises, what is going to happen then? If I'm, instead of using the size in square feet, I'm going to use the size in square meters. Well, we already know as econometricians what is going to happen in that particular case. Roughly, we can say that size in square feet is 10 times as large as size in square meters. So if I have, say, a flat of 800 square feet, that is roughly equal to 80 square meters. And we do already know as econometricians what is going to happen in ordinary squares or standard regression. At the moment that we're going to, well, divide our x value that we've over here by 10, then what's going to happen with the beta coefficient? Well, that will be multiplied by 10. That makes sense because of the fact that we didn't do anything with respect to our feature in a sense. We only divided it by 10. So therefore, in order to get exactly the same kind of model, the beta coefficients should be 10 times as large. Otherwise, xi times beta is going to change, and that is a little bit strange, of course. So you should realize that in ordinary squares, there's no problem, of course, by dividing your x's by 10 or by maybe 100. And sometimes we even do that because of the fact that that will give us actually better, say, beta coefficients. Sometimes these beta coefficients can be very, very small. So then we actually already decide ourselves to, well, make these x's a little bit smaller. That's actually also not a problem at the moment that we're going to look at the lasso or with respect to rich regression. But there is a problem with respect to these methods. And that is that here it is not a problem, but the problem actually arises over here. At the moment that I'm going to divide my x by 10, then the beta coefficients are going to be, well, in order to make the same prediction, they must be multiplied by 10. And then we are going to see that you're going to be penalized 10 times as much in the lasso, in which it's even worse. You're going to be penalized 100 times as much by having exactly the same kind of feature, but just measured it a little bit differently. That could, in the lasso case, mean that at the moment that I have a feature, for example, the size in square feet, and then I make it the size in square meters, that even though size in square feet was included by the lasso, and size in square meters is going to be excluded simply because of the fact that the corresponding beta coefficients are simply too large to include it. Well, that is not good. We don't want, of course, our method to be determined by the way we measure our axis. And that is the reason why, in order to get the best results, that what we typically do is that we're going to try our axis to make our axis comparable with each other. And that we call normalization. What we typically do is that at the moment that we have continuously distributed axes, then we are going to normalize them in such a way that we're going to subtract the mean from them, and we are going to define them by the standard deviation. Well, then you will see that the problems that I just discussed and generally the performance of both ridge and lasso is going to be better. Well, that brings me to the next topic, and that is the example that we already have looked at before. Remember that we had this example of yi is equal to gxi plus ui, and ui was normally distributed with a mean equal to 0 and a variance equal to 0.25. And well, we had this relationship over here. Also, x was distributed uniformly between -1 and 2. Well, now what I'm going to do is that I'm going to use ridge and the lasso, and I'm going to use a polynomial up to the order 50. So I'm going to include x squared, x to the power 3, up till x to the power 15. And in addition to that, to make my regression a little bit more flexible, what I'm going to do as well is that I'm going to include an additional dummy variable for xi larger than 0, as well as an additional dummy variable for xi larger than 1. And then what I can do is that I can now, well, interrelate these dummy variables with this polynomial. That means that I get 150 regresses because I have, well, here 50 regresses. Well, if I interrelate it, then I get another 50 regresses, and here another one. So in total, I have now 150 different regresses. Remember that the sample size was only equal to 100. Well, you should realize, of course, that in a standard econometrics framework, this would be not possible. It would not be possible to have 150 different regresses and a sample size only of 100. But you should realize that that's actually not a problem at the moment that we're going to do either ridge or the lasso. Then at the moment that we're going to look at the performance, well, as I already said, ridge does also in this case outperform the lasso actually by quite a lot. We get a test risk equal to 0.45 for ridge and 0.58 for the lasso. Well, you should remember that that's actually much better than most of the regression methods that we have looked at so far, all of them. Remember that series regression gave 0.59 or almost 0.60. So that's worse than both these methods that we have over here. And you should also realize that linear regression was even much worse than that. So that in that sense, we have improved quite considerably. Remember again that the lowest that we can ever get is 0.25. So we have been able to improve actually quite a lot, especially with respect to this ridge. Actually, ridge even outperforms in this case nearest neighbors, because nearest neighbors got something like 0.49. Well, then finally, we can also look at Gothenburg house prices. Remember that I had a situation in which we had a regression of many, many features. And then I got an R squared equal to, well, 0.79 or almost 0.80. And a test risk equal to 0.0287. This R squared, by the way, was on the test sample, not on the training sample, of course. Then we can do ridge and lasso. I'm going to use here 10 folds. And the results are then as follows. Ridge performs much better than what we have over here. We get a test risk equal to 0.166. And then in addition to that, the R squared is going to be equal to 0.88. And then finally, at the moment that we're going to look at the lasso, well, the lasso here outperforms actually even rich. We're going to see that we get 0.016, and the R squared, well, it's a little bit higher also, of course. There's a one-to-one relationship between R squared and test risk. The, say, R squared now becomes almost 0.89. So we outperform this method of regression quite a lot.